The two speakers of the first debate are Gilles Pigeot-Descabeaux and Roland Pellenc. Gilles graduated from l'École Normale Supérieure de Cachan in 1985, and he got his PhD here in Northwest in 87. His research activities first focused on damage and fracture of quasi-brittle materials and looked at durability mechanics, fracture, and combining damage mechanics with chemistry, concrete and cement. At the University of Pore, he created in 2008 a group dedicated to hydromechanics of porous material. And today, Gilles is directing the hub New Frontiers in Porous Materials, which is a collaboration between University of Pore and Northwest University. Gilles received the bronze medals from CNRS in 1991 and the Jean Mandel Prize of the French Association of Mechanics in 1992. He has been member of the Institut Universitaire de France since 2012. And in 2019, he received the Dolomieu Award from the French Academy of Sciences. He has been also recently elected chair of the French National Committee evaluating research in radioactive materials and wastes. Professor Roland Pellenc is director of the research at CNRS, the French government agency for scientific research, he's visiting professor in the Department of Physics at Georgetown University in Washington, D.C. Roland is a computational materials scientist, and after a master in plasma physics from Aix-Marseille University in France, he obtained his PhD in chemical physics from Imperial College in London, in UK, and that was in 1994. Roland Pellenc's research is dedicated to the development of bottom-up simulation approaches for a large variety of critical problems in energy and the environment. He's the author and co-author of more than 230 papers that are published in major peer-reviewed scientific journals. Roland also was the founder and the head of the MIT CNRS joint laboratory together with Professor Ulm. And he now leads a research effort in France, in Europe, and the US on urban physics, linking city texture as seen through the prism of statistical physics and applied to the environment, public health, and climate challenges. Since November 2020, Roland serves as Associate Vice President for the International Relationship in charge of the US and Canada for Paris Science and Letters University. And Roland received a number of research awards that include the Prix Special du Jour, sorry, my French is very bad, Trophée de l'Innovation from Aix-Marseille University in 2019, the Research Medal of the European Geomechanics Association Alert in 2018, the Young Researcher Award at the French Festival des Sciences and Technologies in 2003, and the Young Researcher Award of the Division of the Physics of the Chimie of the Société Française de Physique in 2012. So Gilles and Roland today will debate a very important aspect of porous materials and poromechanics. As we all know, when we have pores in materials, we have a fluid phase. And in the fluid phase, we might have transport of many different ions and other aspects that are related to the porosity of the material. And the question is really whether the fluid that we have in the pores and the solid skeleton are coupled. And there are multiple levels of coupling. Of course, can be physical, can be chemical coupling, can be mechanical coupling, and this is really the core of this debate. And the debate motion is fluids and solids are not fully coupled in porous media. And with this, I'll give the floor to Professor Pigeot-Descabeaux for his argument in favor of the debate motion.
Thank you very much, Gianluca. Let me share my screen. There we go. You should see my slides now. Is it okay? Okay. So let me start this short presentation the issue is that I will be quite, as a matter of fact, I'm quite comfortable with the motion because I'm almost sure that most of you will vote against. Otherwise, you would not attend a conference in the name of bio, I suspect. But then let me try to detail a little bit what I have in mind when we say that fluids and solids are not coupled in porous media. Let me just for the record, here are the basic equations that we all know, and these are very simplified. It is in the case of saturated porous material, where you have the porosity, the fluid pressure, and the governing equations are equilibrium, conservation of mass as far as the fluid is concerned, and you have also the constitutive equation, whether it is linear elasticity, nonlinear, and any type of constitution you might think of, where the total stress is the sum of the contribution of the fluid and the contribution of the solid. You have the equation of Darcy's equation that governs the flow of the fluid, and of course also you have the variation of porosity. Just for the record, so that we all have in mind that within this format everything should be coupled. Now these are the equations. The reality, let me first start with a very simplistic example: gas production. What people do, at least in the industry, where they design the exploitation of a field. Here it might be it's supposed to be a gas field. Let me just get a pointer there, where you have wells that produce and wells that inject. And what people are worried of course, you have all this is all the hydrocarbons are contained in a porous material, in a reservoir, in a rock, in a porous rock. And what people look at, just to look at the permeability. This is an important parameter to them, and they absolutely don't care about the effect of stresses. In most cases, I would say this would be it is a generality, but usually, at least at the industrial level, from a very pragmatic point of view, when you design the exploitation of a site, you don't worry about stress. Still, you have a porous material. Let's consider something which is a little bit more complex, and this is dealing with the safety of nuclear vessels. A couple of work that we did when I was in Nantes a few years ago, where we were concerned with the internal vessels, specific design in France, whereas these vessels are made of pre-stressed concrete. You have a double layer vessel, and both are made with pre-stressed concrete, or one is reinforced and the other is pre-stressed. Concrete is the third passive barrier in the safety design of such vessels, and it is monitored with decennial integrity tests. Basically, what they do is they apply a pressure inside the vessel. Of course, they stop everything. They apply a pressure, and they measure the leakage rate. And if the leakage rate is above a certain threshold, the facility cannot be restarted. So the issue is to evaluate a potential leakage, which is due to the aging of the concrete. And here you would expect that there is a strong coupling, at least between the solid phase and the fluid phase. The solid phase is made to to prevent the fluid to go from inside to outside the vessel. So typically what is being done now, it has been most probably a little bit improved, but not that much, because these are rather complex structures which are pre-stressed with passive steel bars, concrete, just considering a representative volume like this, and then you apply the pressure inside and you measure the leakage rate outside. And what is currently being done is first a mechanical calculation. Due to the internal pressure and the boundary conditions, you get some whatever mechanical model you want to apply. Here it's an elastic plastic damage model, and you calculate damage, the effect of the damage which results from the internal pressure on the vessel. Then you take into account the drying effect, and you perform a calculation of the profile of humidity, which is there. And you plug all this, and separately you perform a calculation of the leakage rate based on the gas permeability. So you convert both information from the mechanical model and the hygrothermal model into a relative permeability to gas, and that provides you with some calculation of the leakage rate. So here there is some coupling, but in fact everything is uncoupled. There is some coupling in the sense that the amount of cracking, the quantity of fluid, of liquid, which is contained in this representative volume has an effect on the fluid flow, but it is not coupled. It is just a one-way coupling. Some more complex example. Here I took the case of adsorption of a single gas in a porous solid with many applications in the industry, and that concern carbon, but also cement paste, tight rocks, and many other porous material. The issue is that in this case, the fluid, which is here in small pores compared to mesopores and macropores, you have micropores in size of a few nanometer at most. The fluid that is concerned is confined by the solid phase, and it is in a different state as compared to the bulk, the fluid in the bulk phase. Different state of pressure, different state of mass density. And that produces a very unexpected response. That is, if you take this piece of porous material, you put it in, you saturate it with a fluid, with a gas, you increase the pressure, instead of shrinking, it is going to swell. And this has been measured quite a long time ago. Here you see some results of Levin in 1996, measuring the swelling as a function of the pressure in the fluid. And you see that you see this unexpected response, which depends on the type of fluid that you have in the porous material. That can be also simulated. Here it was simulated with help of Monte Carlo simulations. And in fact, what you obtain in the case here, where you have a slit pore, you have the spacing in between the pores, you are getting enormous pressures, fluid pressures inside those micropores. And what is most important is that depending on the opening here on the width of the pore, you have a very different pressure. Going back here, you would see that deformation can amount to, let's say, 1%. If you look from this curve to this curve, you have something which is 5% of deformation. So you would expect that here, the fluid, the pressure in the fluid really depends on the deformation. And that is almost never taken into account in existing models, where in fact you compute the real pressure that is applied inside this inside the nanopores as a function of adsorption. You calculate with a standard poromechanical model, and hence in this case with the effect of adsorption, the swelling. That provides you some results which make sense, but I have not seen, to my knowledge, results on how the permeability would be affected by swelling. In other words, you have pores which size changes, and that does not affect the permeability. And in this type of calculation, where you would expect that you have strong coupling between the fluid and the solid, in fact, the solid is assumed to be rigid as far as the fluid is concerned. And that is not a coupled scheme. It is coupled, but not completely. So what I would like to conclude with was that in most practical examples, you have indeed coupled effect, but they are not important. Whether there are second order effects or not, I wouldn't dare to say, but they are, for practical purposes, not very important. When coupled effects are important, in most cases, it is a one-way coupling. It is not a two-way coupling. And I believe that Roland is going to share with us cases where you indeed find such a two-way coupled effect. Thank you very much.
Excellent. Thank you. Thank you. Thank you, Gilles. And now is Roland for
Yes, sir. Here I am.
arguments
So,
against.
so who's sharing? Gilles, you maybe have to stop sharing your screen. Yes.
Yep.
That's done.
Yep, very good. Now I need to find out my presentation, do something else, maybe here. Yep. How's that desk work? Yes, it looks like we have some. Very good.
Perfect.
All right. All right. So, well, thank you for the invitation. And
can you invert the screen because we are seeing the.
How do you do that?
If you go to the top, there is swap display.
Where is it? To the top? Yes.
To the top, there is swap displays.
Stop video. Where is it? Oh yes.
Swap.
Switch. Yeah. Yes. Yeah. Okay. Yeah. All right. There we go. Very good.
Excellent. Thank you.
Because I have two screens there. All right. So, well, I was saying thank you for the invitation. And actually, I was wondering about that format. You know, this kind of debate idea. And at the end, it turns to be interesting, actually. Obviously, I'm not opposing Gilles in what he was saying because it's obviously interesting. I have taken, so the idea was Gilles to take the kind of the side of the solid matrix and me more where I'm coming from, which is the side of the confined fluid, right? And see how much the fluid is influencing the matrix and how much the matrix is obviously influencing the solids. So this is a kind of the way I'm going to go through this question to see and answering obviously at the end some yes. All right. So so what? Yes. So maybe here. Right. So next, talking about porous solids, I want to go down to what those are. Obviously, you can take like simple ones. I mean, simple ones, not so simple, but I'm saying simple because they are crystalline. So those zeolites. One of the leading members of the zeolite family, which is a family of 500 members, is the one called silicalite. It's been used in the oil industry to convert methanol into gasoline and so on. So the pure silica stuff, but you see, this is very ordered. That's the sketch of the pore network, and the size of the porous is typically 5 angstrom, half a nanometer, very small. Then we have the messy ones. Then, for instance, porous carbon, still the same kind of pore size, but then this is really more like a glass. There's nothing like a order in there. And in the past, I was involved in developing the first models of those 3D models of those porous carbons, to move away from the assumption that they were graphite or graphene-like layers, because they are not, in fact. Okay, so we are in a very tiny pores. Well, we call what I call nanoporous, what is referred to in the literature as microporous. But don't get me wrong, most of you are mechanicians. Microporous in this case means nano, not micron, okay? So microporous is less than 1 nano and 2 nano. It's actually for a very good reason. We'll see that in the next slide, that the fluid is so confined that the matrix itself just kills any phase transition for the fluid, just to tell you how much it does influence, the solid influences the fluid. The solid influences the solid. Now let's go bigger in the terms of pore size, and then you end up with considering those porous glasses like Vicor, same like silicalite, purely silica. Pore size kind of messy, connected in 3D, but with a kind of not a very pore size distribution very wide. The pore size of Vicor is typically in the range of a few 4 to 8, say, nanometers. Then obviously you have other samples, like then I go down to more ordered, I go to those MCM SBA, so still silica, but they are made from soft chemistry, where you do this ordering of an organic phase, surfactant phase, and then you just burn it, and at the end you're left with the porous matrix, and these are proper cylinder. So I have to say that the walls are actually not crystalline, not a crystal like zeolite, but the pore size, a few nanometers, is controlled by the size of those organic molecules, if you like. And it's interesting because these are not connected. This is the most ordered thing that we can do. When I say ordered, they are not necessarily, I have to say, smooth in terms of along the channel. Could be some roughness, obviously, but okay, that's what we have. And obviously, we have those two very dear example, which are soil and clays, for instance, clay momonite, where you have a swellable system, clay that does swell. Depending of the, and so the amount of confined fluid in between the lamella is changing. By the way, this time, the confined fluid is an electrolyte, meaning solvent, water, for instance, and some ions. And the most interesting thing is that, I mean, obviously those layers are charged. That's why you have ions, and the ions are driving the intake of water in the system. So it's a kind of a very coupled way to say things in some ways. It's a very coupled system. Now, and then we move on to cement or tobermorite. Tobermorite is not really cement, is a mineral per se from the island of Tobermory in Scotland. And this is actually a layered system like clays and charged. So again, you have ions in between the layers to maintain electron neutrality, and the water as a solvent getting in because of the ions. All right, so let's move now to other concepts. Porous carbon is probably multi-scale. For instance, this is a porous carbon. This is a piece of wood at the scale of, say, almost a millimeter, say, 100 microns, and you see the cells of the wood. And now you dig down and you see some structure appearing in this wood thing. This is, I mean, this is burned wood, actually. This is a charcoal, right? As we go down, we zoom and zoom, you see other texture appearing. All right, at the scale of 1 micron, it's kind of, you don't see much, but yes, there is substructure, because if you zoom again with a TM microscope this time, not a scanning electron microscope, you start seeing nanopores, clearly, and up to that kind of range where you see at the scale of angstroms. So I'll tell you that those natural porous materials, as opposed to zeolite or things, even though are multi-scale. When I say zeolite are just one scale, it's not true, because you can gather grain of zeolite and then you build up naturally a multi-scale porous material. So the multi-scale is important because certain things can happen at certain scales, and more and not at other scales. All right, so that's one key element, and the second one, this is, sorry, the further zoom at the scale of angstrom this time. Yeah. All right, confined fluids. What kind of fluids? All right, molecular fluids, of course. Water, cement, and clay, cement, and so on. Could be hydrocarbon molecules when we're dealing with shale and so on. I said that cement is water and ions. It's called an electrolyte. Okay, that is a key. I mean, a key step, having those ions to maintain somehow some electron neutrality, because it does influence a lot the coupling between the fluid, the electrolyte, and the matrix itself. Could be covalent fluids. Why not? All right. So these are you can build. It could be metallic stuff and so on. So today I'm going to clearly focus on molecular fluids. All right. All right, so to what I just said, okay, for a long time, any modeling of those porous material, we're assuming pore with a given geometry, a given type of geometry, cylinders or slit pore on the left and right, with a given size, maybe with some distribution, a pore distribution, but in every of those kind of attempt to model a porous material, those pores were not connected. All right, so something to bear in mind. And this is where there's actually this ranking of pore size comes from. It comes from a paper in 1985 from the IUPAC, which is the International Union of Chemistry, that produced this kind of rule, saying that micro is less than 2 nanometers, meso pores is less than 20 nanometers, and all above is called macro pores. The reason for that, and there is a reason, a physical reason for that, is that when the confinement becomes so strong, it kills any phase transition of the fluid. The fluid is really, the way the fluid structure in the porous material is entirely due to the interaction with the solid. All right. When we're in the meso range, we do still maintain some kind of phase transition, such as the capillary phase transition, also known as capillary condensation or capillary evaporation, depending on the way you put in and take back the fluid. And that is actually not the bulk one. As we'll see, that is totally shifted. So this is, again, a way to see that the solid does influence a lot the confined fluid. And the macro system, the macro pore, is typically when the fluid is, I mean, the pores are so big that there is no confinement effect. And basically, we have the phase diagram, the fluid as the phase diagram of the bulk. All right. Now, I want to understand, obviously you understood that we can play with different sizes, and we can play with the texture in terms of order or disorder. And this is an old slide that I've been presenting for maybe 20 years now, when you can actually, on this x-axis, go from ordering system to disorder, from MCM41 to Vicor, and going in terms of pore size from zeolite to mesoporous system when you go on the vertical axis. All right. Okay, that's a very usual plot. I'm going to spend some time because this is typically when you put some fluid into a porous system, people want to measure. He wants to measure that. Why? For good reason, because this is the adsorption isotherms, meaning so isotherm means at constant temperature. And adsorption, it means that this is a physical process that brings a fluid to a surface or to a porous environment. First, and there are different type of those adsorption isotherms that are said to characterize the type of environment. Say that we consider curve number 2. This is the curve of a open surface where the fluid actually likes the surface. And you see that as you increase the pressure of the fluid, you see adsorption taking place. You have this curve with a B point. We have a knee forming, right? That corresponds to the building up of a layer at the surface of the pore. So you see that already that the fluid can be in the gas phase far away from the surface, but it's already in a very condensed phase due to interaction at the pore surface. Right? You say, okay, but what happens now if the fluid doesn't like that surface? But then we go to plot number 3. This is typically some kind of fluid that doesn't like the surface. You're not building up this molecular thing. So for instance, that could be actually where water doesn't like some substrate, and at the end, you need to pressurize water to the liquid phase outside, I mean, so in the bulk, so that in the end, you have a condensed fluid somehow in contact with the surface. All right. Now I will comment plot number 6. 6 is this wavy one. That wavy one is a bit like plot number 2, but when the surface is so well organized with no defect, no cracks, no lacune, no dislocation, nothing, that the fluid can actually piles by in a very defined layer structure. That has been observed, for instance, for I think it was methane on some MgO, magnesium oxide surface. Argon, I guess on graphite will do the same. You need to have a super well-defined surface. And then you start piling up, and then every step corresponds to a 1 atomic size layer of the fluid. All right, now we move to porous material. If you take a meso-porous material, I was showing what this is, as I said, a pore size where we do maintain phase transition. So that's typically what's happening in plot number 4 for a solid porous, mesoporous, where actually you have capillary condensation, and that is characterized by that hysteresis loop. So on the way up, we don't take the same path. On the way down, when we increase the pressure, we suddenly have the building up of this film of the B point and so on, and suddenly the pore fills up with totally with liquid. When we depressurize, we try to take out the fluid. The pores, the fluid doesn't go through the process doesn't go through the same path, and we have this hysteretic behavior that is fully connected to the fact that we have a first order transition of the solid, of the liquid, sorry, the fluid inside the pore system. But what is interesting is that this capillary condensation is actually not the bulk one, because it obviously occurs in the bulk, but it's actually shifted towards lower pressure. All right, and curve number 5 is the same thing for a solid where that doesn't like, I mean, there is no building up of the fluid, and we need to condensate the capillary condensation by pushing, for instance, from the outside, and actually the filling up with the liquid kind of occurs when the liquid is already from outside in the bulk. So this is above P over P0 equal 1, actually, P0 being the saturating pressure. And then we have number 1. Number 1 is so-called the Langmuir adsorption isotherm, which is typically always happening in very tiny pores where there is not much of fluid-free interaction. Okay, and everything is driven by the fluid and the surface. And this typically was happening in zeolite, in porous carbons, and so on. And on the way up is equal to the way down. So there is no hysteresis loop. And just to tell you what I was saying just before, that the confinement is so strong that it kills the property of the ability of the fluid to go through phase transitions. All right. By the way, I'm talking about the gas phase, the gas liquid phase transition. The other solid liquid phase transition will obey the same kind of behavior, being shifted to a lower kind of other parameter or lower driving force. For instance, the temperature in the case of the melting and the temperature, the transition, sorry, but we have the same kind of ideas. So too small kills phase transition. Now, I want just to illustrate something with a concept that is used by everyone. this concept of specific surface area. So the idea is what? Is that so supposedly the fluid is supposed to cover all the surface in one monolayer film. Why not? If you know the size of one molecule of the surface, then you're measuring the surface available to the fluid, measured per grams. You have a number of meters squared per gram. This is the specific surface area. Some years ago, with Pierre Levitt's colleague from Paris, we did this calculation. So these are simulation where we were doing the specific surface measurement. We're using grand canonical Monte Carlo simulation of very simple fluids in actually for different rare gases, neon, argon, krypton, xenon, into Vicor. Vicor, that's porous glass, mesoporous. So we were measuring the beginning of the isotherm, so to say that we are measuring the surface. And it turns out that you see that there is a linear dependence of the specific surface area, this geometric quantity that's measured by everyone, as a function of a specific property, which is called the polarizability. In this case, very simple, because when you write the interaction of those rare gases with the surface, this is the only term that attracts molecules to the surface. This is called dispersion interaction, also known as the van der Waals interaction, and that is proportional to the polarizability of molecules, right, interacting molecules. So you see that what's interesting is that if you do the adsorption of xenon, you have half what is measured by argon for the same substrate. And why is that? It's because argon does wet the surface, wet in the sense that he wants to cover all the surface. He likes going to the adsorbate so much that he actually covers the surface. Not the case of xenon, not because xenon doesn't like silica, it's because xenon likes the other xenon more than silica. So in the end, xenon produces small, very nano droplets everywhere into some curvature of the surface without covering very much the surface in a very homogeneous fashion. So xenon is not good to measure specific surface area. So you see, by just that example, you can see that the interaction is really driving even the building up of a monolayer or a few layers of molecule at the surface, obviously, even porous material. So now coming back to differentiate between nanoporous and mesoporous. For instance, this xenon in this zeolite silicalite. So I can remember the blue point were my simulation, the green the experiment. So we can very easily how to say, predict, say, the thing. And there is no nothing heroic in that, because silicalite is a crystal. You just download the crystal atomic positions, and you're done with the simulation basically. All right, so porous carbon, this is here a plot from the second from the PhD of Benoit Coaz. This is argon in porous silicon at 77K. So you see, as I said, the physics option and the capillary condensation, which is obviously absent when you are in very small pores, as I said earlier. And those porous silicon are a very nice, well-defined pore size of 10 nanometers. All right. So what's the difference between, what's the influence of disorder and pore conductivity? In this case, I will compare the adsorption isotherm of argon at 77K in MCM41 and Vicor. These are experiment data, by the way. And you see that for MCM41, we have this very, very vertical hysteristic loop. As when we move to disordered system, we have this gradual filling up of the disordered system and a sharper desorption line. There are very good reasons for that. It's actually the desorption line is at equilibrium. It follows the Kelvin equations. The adsorption line in Vicor is just showing up the fact that you have different environments. So you have a kind of gradual kind of filling up of the pores, some there condensation, in other part no condensation. At the end, you have this very smooth signal on the way up. But on the way down, this is basically a desorption that corresponds to the Kelvin equation. All right. If we dig into the physics of that, it says the work that was done in the 80s, 90s by those people, Evans, Gubbins, and so on, is that using different theoretical approach in molecular simulations, that this is a real first order phase transition. And for instance, for an infinite tube, you have this sigmoid type of van der Waals equation for the fluid that is shifted from the bulk, obviously. And if you write the quality of the two areas when you go up and down, the Maxwell construction is called, then you can localize the equilibrium. And the desorption line corresponds to something called cavitation. You break the liquid, actually. So you depressurize the liquid to a point where it breaks, basically. But then Maddox and Gubbins show that if the pore system actually has a finite length, which is the real thing, obviously, then actually the desorption occurs at equilibrium, and then you don't see this cavitation thing. You go through the equilibrium. All right, now let's move to temperature effect. Actually, this is the very, very important work of Morishige back in 2004 with it in MCM41. When you see that you increase temperature, the hysteresis loop disappears, and yet then you switch from a discontinuous behavior to a continuous behavior, adsorption, desorption wise. And that again fits very well, fits with the concept of phase transition, first order, but shifted. So tell you that the fluid does influence a lot. The solid does influence a lot the liquid, even in those kind of bigger pore where you can still have a phase transition. The plot on the left is a recent work that we published with this is the PhD of Siawash Monfared, who is now at Caltech. He was with us at MIT, and this is the shift of the critical point of the confined fluid, because the confined fluid is nevertheless, although it's experiencing a phase transition, is not the bulk one. So there is a new critical point that is due to confinement. You see, again, the confinement, the interaction shifts things. And what's interesting in this work, besides all the points that you can see, is that we have this linear behavior of the shift critical point with 1/r, the pore size. Sigma is the molecular diameter. And what's interesting is the orange point here. If the solid is kind of dilute in the sense of not very packed, like a granular system with a packing fraction of 0.5 something, around that point, then actually most of the time the correlation length in the liquid is the same as in the bulk, and there is no much of confinement. So in this case, there is less coupling. All right. So this is what we're saying here, the kind of a resume of the whole behavior. You have below the TCC, which is the confined critical point, you have the hysteresis behavior that disappears when the temperature is increased to TCC, and obviously we keep this reversible behavior above TCC. All right, so that, forgot about that thing. It's just my point that you can write down this free energy stuff of a fluid layer in equilibrium with the gas phase. Very simple. You have a kind of surface term and volume term that's coupled through this exponential term. If you write down the FR, which is the free energy of the system, that's the exponential term. And then when you go down to everything, you can derive the Kelvin equation, which is at this equilibrium relation that you see in the bottom, with a term here that actually kind of is the correction of the Kelvin equation when you go down to very nanoporous system. And obviously, the breakdown of that is when you reach a pore at a given temperature so small that you don't have any phase transition. All right, so it does work pretty well. And that was
Roland, can you please wrap it up?
Yes, I'm almost done, actually.
You.
All right, so just to tell you that it does actually, you can see that with the molecular simulation point here, that you have this curvature, and the line is the Kelvin equation. So the Kelvin equation should be taken with care because we need to correct for the gamma with surface tension, which does represent the surface tension. And then I'll come to a porous mechanics, because I cannot say anything, forget that, which is, yes, the fluid does actually modify the solid and in terms of swelling and shrinkage, and this is typically what the people have been doing that, and related the solvation pressure, which is the pressure of the fluid, to the strain experienced by the matrix itself. All right, and you can read the papers of Gennady Gore or Alexander Neymar. These are good authors to read. All right, we did the same kind of pore mechanical system for granular system in cement, and we have the hysteresis loop, and within the hysteresis loop, we could calculate the shrinkage, the strain due to the capillary forces bringing the grain together. All right, that's the work of Edmond Tingtao Zhu some years ago, 2 papers. All right, and then my last slide will be about what about the zeolite stuff, and this is my encounter with Poromechanics, 1995, where I was trying to simulate this curve of argon with the step in the adsorption algorithm, and I didn't get anything. That's my green point. When they were shifted by a lot of magnitude, and that was not a swelling, by the way. It was a change of symmetry of the solid. That's clearly the fluid did change the symmetry of the solid. And just to add on that, people in Russian were doing way before me that they knew that the fact in very small pores you can absorb fluid and they can actually shrink, or depending on the pressure, shrink or even make the thing to swell. All right, so same for porous carbon, right, that we did with Laurent Brochard some years ago. And then I think this is my last slide, Are the fluid and solid carbon porous media? Of course, my answer is yes, indeed. Thank you.
Thank you. Thank you very much, Roland. Very stimulating presentations. We, of course, now have a lot of time to ask questions, debate. I have a few questions, but for the audience, please write your name in the chat so that I can then moderate and call you for questions when the time comes. Now, to be fair, I think Roland went much longer than Gilles, so I'll give Gilles first voice to react to Roland's presentation, and then I'll go and ask questions. So Gilles.
Okay, thank you, Gianluca. Well, yes, of course, I do agree with what Roland just described, but let me, if I would summarize, yes, the fact that the fluid would interact with a surface which is part of a pore has an influence of the fluid. But how about the solid? The only example that I saw was when it was a change of symmetry, when in fact, I would expect that because the microstructure of the solid would change, then you would have a change of mechanical response. This might be the only case where I saw in your example that you had a two-way coupling, a coupled effect, if I may. That's my comment.
Okay. Okay. So I should actually, I was a bit short in this explanation. Yeah, that was my first encounter with Poromechanics, with the change of symmetry of the zeolite because of the fluid. Fine, but it's my own little story. But now, I mean, first, as I said, the Russian knew from the work of Kiselev that, you have, imagine a very small pore, you have a molecule in between, like a very tiny pore. Actually, the pore will contract first before, because it brings the thing to a more attraction before actually swells when you start filling up the repulsive part of the potential with the solid. So this is for zeolite, this is contracting and swelling, so very big. And since then, because we are been in business for some time, those MOF, those metal oxide framework appear. This is there were like the beauty to do Poromechanics, because those things they can shrink reversibly by 70%. So the people have tested all the theories I'm taking. People are Alexander Neymark, will be Anne Boutin, Fix Couder, and Alain Fuchs on one side. Many people have used those metal oxide framework, and you can see this, as to say, the breathing, depending of the fluid of that thing, from a very collapsed structure to a very expanded one, and very reversible, in a very reversible way. So that is really more than like just a change of symmetry. You have a change of the thing by 70%.
Yes, but then in this case, even in the case of MOF, metal oxide framework, do you change the constitutive law for the fluid motion because of the pore size changes, for instance?
Yeah, but okay, when you say
people
changing,
don't do that.
It doesn't change to the point where you have a phase transition, for instance. We are still in this nano, whatever, a few angstrom, say, okay? So this is the same fluid, if you like. Yeah.
So it's a coupled effect on state variable in, I would say, some type of reversible regime.
It is.
And in most cases, when we deal with internal variable with non-reversible regimes, its coupled effects are much more difficult to account for.
Of course, I tell you the more
and they are ignored simply.
So, for instance, when you go on your line, the magnitude of things, some guy from Grenoble in France were measuring the capillary condensation, the strain imposed on porous silicon from the capillary condensation. So porous silicon, the walls are crystalline, so you do diffraction, you can measure the displacement of the peaks, and you know exactly how much the thing is shrinking. Okay, it was in relative effect by 10 to the minus 4. Okay, so between 10 to the minus 4 and by 70%, you have a window of things. So, but what's interesting is that in my old days when I started my PhD, what kind of books there by James Barrer from Imperial College, where I was, and also from Ken Singh. And if you read those books, they were assuming that nothing was moving. I mean, that the porous material were fixed forever. And you know, it took some time to implement, and that actually the pore mechanics was and is still the new frontier of porous material, really.
Yeah.
Okay, it was ignored for a long time. But, yeah.
Very good, very good, very good start. I think I have here a question, Professor Ulm. Franz.
Yeah, thank you very much for the reenactment of the French Revolution here. I have two questions here. I think one to Gilles and the other one to Roland. Gilles, the equations which you have made your whole argument on are, in essence, the solid state equations, right? You have a stress eventually related at the boundary to some pressure of the solid, which then ends up in the classical poroelastic or equivalent or poroplastic or pore-damaged plastic state equation. Look, since this is a boundary condition, are we not limiting ourselves because of the fact that this is a boundary condition, so which satisfies the normality condition of classical continuum mechanics? Are we not in your conclusions that the two-way are decoupled? Is that not due to the fact that you simply impose a boundary condition on it? So you know it a priori in order to come to the state equation. Otherwise, that is the ensemble, the first point here. That's my first question to you. The second one here, you evoked it slightly in the terms of when you said, let's say, what's the order of magnitude, how it does change, right? Is it because you operate in small perturbation, as you would say in France, right? Small perturbation theory, where you have small porosity changes, small XYZ. Is it because of the smallness of it driven by the application that you don't see the two-way coupling? So that's my question to you, Gilles. And then I will ask my question to Roland, if I may.
Just to answer a quick answer to the second question, you're totally right. It is just because, I mean, in my opinion, that we are looking at small perturbation, and therefore coupled effects are very often second order effect, unless it drives to irreversibility, dissipation, and then it may become of higher order. But if you take it as such in a classical framework, it will be in most cases second order effect, because we are looking at small variation of porosity, and therefore we are looking at small variation of pore sizes, and therefore you have small effects on the fluid transport and so forth. That's for sure. Now your question about boundary condition and normality.
So maybe to be more specific about it. So when you take a solid material, you take the solid phase, you impose on the boundary a pressure times the normal as a boundary condition. You upscale this here with in the classical way how we do things. You end up with and assume an elastic behavior. You basically end up with the bio. With the expression, with the state equation of bio. That's basically the idea behind it. So my question here is, since the fundamentals of the continuum model is the micromechanics boundary problem there here, is it then that because from mechanically speaking, a boundary condition is something which I master, is it then related to the choice of the system? Otherwise said, to the choice of the Helmholtz energy, that you derive all the equations, that you simply mask some effects and they will appear in the fluid side somehow, and you artificially break by imposing these boundary conditions the system apart? It's a question, I don't know the answer.
I'm not sure that you can say it is a case, because if you would do it, if you would forget for a minute the microscale, and do it from a phenomenological point of view, and just, you see, write the equation with all the coupled terms, all the possible at the macroscopic scale. My point was that these coupled effects may exist. I do not say that they do not exist, but it is very seldom in publication that people do 100% of the job. When I see publications where people worry about, I mean, I would say the effect of damage on permeability, I almost never see fluid transport calculations in the meantime.
Okay.
I mean, look, just presenting the two results, the complete picture, instead of just looking at one picture, make me say that either they the complete picture is not important, or that we are making a mistake.
Okay.
That's,
okay. Thank you. Thank you. Can I now ask the question to
and
Roland?
the issue of upscaling is, I would say, totally different, because the upscaling indeed may direct some towards some specific coupled effect that would have some importance, and you may forget some others. But if you forget some others, it is because at the microscale they are not important. That would be the answer.
Well, so just to close this, because it allows me also to make the link with Roland's presentation. When you focus on the solid as your reference thermodynamic system, and that's what you do when you do dimension essence, you basically take away all the couplings with the chemistry. Or no, you impose all the couplings actually as boundary conditions. In contrast, if you had chosen another ensemble, and Roland, when he shows the results which he showed, are all based on grand canonical simulations, so he has an open system, etc. And that actually is another ensemble, meaning also another energy functional which you minimize.
Exactly.
And this is, so my question to you was whether it is because of this particular ensemble definition that you say, but you say, I think the answer was clear. Roland, I have a question to you, because I mean, you went all the way to all these isotherms, and clearly for the isotherms, the chemistry of the solid makes all the difference, and the pore size, etc. But are there not a few much stronger examples you have looked at? So let me bring the two which I know you worked on, and I think one is the swelling of coals, where I believe the deformation of a solid, and now I speak about really the solid backbone itself, entails and not a second order, but a first order impact on the very storage capacity, meaning, so that's number one. So it's an order of magnitude here. And the other one, a little bit more subtle, is your work on ice and cement, right? The electrolyte pressure using versus the ice, and basically limiting the ice being a solid here, turning into a fluid when the electrolyte pressure comes to it. Can you share this coupling, actually, I think, which is, to me, a very strong coupling in both effects with us?
Actually, this is the first time, the core example is actually the first, I mean, my encounter with the work of Gilles and Romain Vermorel before he joined MIT, actually. And this is, I have in mind this work of experimental from Massotti from ETH Zurich. He's the one who's doing measuring the strength. So it really depends on the fluid you put in this source, in this charcoal. For CO2, you have a swelling by 5%, which is huge. 5% is just incredible. Then for methane, you have maybe 1%, and when you put helium, you have 0. So that shows you that the interaction, the way the fluid organizes itself into the matrix, does something to the porous material. And I come back to my argument with zeolite that you don't see for charcoal because of disorder. For zeolite, before going to swelling, you go to a contraction. You see what I'm saying? So this is a very rich behavior that depends on the organization of the fluid and also the type of the energy, the adsorption energy in the end of the particular fluid to the particular surface. I mean, pore. Now, you bring me back to this ice idea, and the idea is the following: is that we were looking why cement degrades at -7 degrees Celsius. All right, the pore size of cement pores, I mean, you know, the cap, and we know from the work of Jason Weiss that you need to have 80% of the saturation of the paste with water to see some freezing damage. 80% means that we are playing with super big pores, like capillary pores, like tens of nanometers. As I said, I mean, the bigger the pore, the less confining effect you have. So what is cracking cement? So obviously that goes with this idea of ice occupying a larger volume, but then we show that the porosity of cement being totally connected to 92% using those tomography experiments, that actually was more like the building up of, it comes down to a nano problem where the ice doesn't like ions, the ice doesn't form with ions. So all the ions in cement thing were actually confined in this region in between the cement and the ice. So this region is never going to freeze because of the ions, and that creates this pressure, this disjoining pressure that actually prevent ice forming, if you like. So for some time, nothing happens, but then temperature drops so low that this interaction, this electrostatics interaction, then creates a stress that is in the end transmitted to the cement paste. So you see, this big pore problem becomes in fact a nanoporous problem, a nanopore problem between the ice forming on one side and the cement on the other side, and that layer is a few nanometers.
Very good. Thank you, everybody. I don't see any names in the chat, so please, I encourage the audience to ask questions. I do have one question. I have a few questions actually, and one is, I think Franz mentioned it, to some extent a little bit of that, is that in classical poromechanics, the solid and the fluid are sort of not chemically active. There is no reaction between the solid part and the fluid part. That is, of course, in many cases not true. And concrete and cement is one case. You mix, cement, anaerobic cement particles into water, and then chemical reaction starts to occur. And so you have an evolving system, and it's even what is solid and what is fluid that eventually changes over time. So how does that change your arguments from the point of view of the solid for Gilles and from the point of view of the fluid for Roland? Gilles.
Well, I mean, we saw it this morning with Professor Bazant's presentation. I mean, the case of hydration is sort of archetypal. It is a case where, in fact, the fluid and solid are going to react together. And then in this case, I believe that there is a very strong coupling. I mean, trying to answer to your question, in my opinion, there are at least two problems that we saw this morning where coupled the factor are important. First problem is where indeed there is some sort of chemical reaction between the fluid and solid that are present. And the second case is when you wait long enough so that second order effect can become first order effect. And this is typically the case of long-term creep. If you wait long enough, those tiny effects that you would have at a scale of a few days become so important, then suddenly fluid and solid become strongly coupled. I think these are the two cases where, I mean, it is quite obvious that indeed the two needs to be coupled completely.
So my answer, I mean, Gianluca, you refer to building up bonding, I mean, chemistry, right? In the sense of breaking a molecule to do something with the solid, right? Yes, which is the case for this hydration of whatever, when you are always group attaching, so whatever. So yeah, actually, I like very much to link that with how much a wet fracture is helped by the fluid, in terms that, this is the whole work of Sidney Yip at MIT. He was showing that on the road, a silica road, right? The strain, the stress, because the road is not happy, if you like, there's a lot of stress in there. The water was actually helping by reacting to cutting the SiO bonds, right? And I have the same idea with the fracture. Imagine at the bottom, the very edge of a crack is so confined that the silica SiO bond is ready to react, and the water helps. And then it does always group the surface, and then it helps the fracture propagating. So that will be the kind of where I see really where the chemistry is in action in those porous material. For what I said during my presentation, it was all about adsorption, meaning that all those changes in the fluid or in the solid were made without any chemistry. Like purely, everyone is maintained. But if you're asking me about what if the chemistry is acting, I would say yes, of course, it can even help to the failure of the material. Yeah.
Thank you. Any
question?
Like yes, Professor Bazant, please.
Just a comment, very interesting discussion. What Gilles said, Gilles Pijolier. I fully agree. If you consider vibration, high frequency, complex modulus, surely the solid and fluid are coupled. You consider very long periods of time where water can freely move to the pores. So then probably mostly uncoupled. That depends very much on the rate. That's, I think, basic. In fact, these bio-equations also apply if you reach equilibrium, which means water will move out to another equilibrium state.
Yeah, so I think Professor Bazant's point is well taken. The time scale of the different phenomena that you're simulating or considering, whether it's on the fluid side and the solid side, if they are similar or very different, that will make a difference whether you have a coupling or you can consider at least approximately from practical point of view uncoupled. Right?
Even if chemical reactions involved, still it takes some time, some rate, right?
Yes.
So that's again, you cannot escape the rate effect here.
And so on the same line of inquiry, I think we'd like to, and I think we addressed some of this already, but we can dive a little bit more into the issue of non-linearity of the material. A lot of the work, the theoretical work, assumes the solid to be elastic or maybe plastic, but very few consider fracture, damage, and the real two-way coupling. And Gilles, you had an example in which, for example, for the leakage of the power plant, you can do the cracking, and then when the crack is there, of course, you account for the cracking on the permeability, and then you do the permeability problem, and I think you're probably fine. So what are situations in which you think, and this is for both of you, this decoupled situation or series coupled in a way, it's one-way couple as you call it, is from damage versus the fluid flow is acceptable and when it is not. Okay. And are there just the case-by-case basis, or can we have some general way of assessing where it's critical to us to consider the effect of cracking and damage on the flow, and when we can actually do it separately? Gilles?
Yeah, I mean, I guess that what we just mentioned, the time scale, is probably the most important thing. One issue that I'm always, when you look at those isotherms that you show, Roland, people, by definition, isotherms are provided at equilibrium.
Exactly, yeah.
And how long does the equilibrium takes to get installed?
Okay, it depends on the fluid. Yeah, okay.
It depends. We have been running experiments in the lab. I don't know if Laurent Perrier is around, but and also others. But you may wait for a very long period of time in order to get this thing.
If you take a 8mm wafer of cement paste, drying takes 8 hours, right?
Oh, yeah.
So you would need to go to get, you have to wait significantly, or you would need something go way below 1mm thickness.
Yeah. So the most important, what tells you if it is uncoupled or not, is in fact the time, the kinetics.
Yes.
Time to equilibrium. Unless you're not interested in equilibrium, because also, there are other issues of that couple fluid and solid in wave propagation, for instance, but we didn't speak about that with nonlinear effects. But it's the issue is kinetics. One example on the effect of chemical reaction. A few years ago, we were wondering about the effect of calcium leaching, and we developed in concrete structures. That was for nuclear waste storage facilities. In this context, we were assuming that the chemical reaction would be instantaneous. That makes sense because the time scale of the problem is 300 years. So the kinetics of dissolution of calcium hydroxide in cement paste by water is much faster than that. So you can say, okay, it is coupled. But then if you look at what happened over a day, it has absolutely no influence.
And,
so kinetics is most important.
I think also for concrete, for example, is it really possible to eventually reach the equilibrium. You know, if you think in terms of concrete, non-cement, you know, cement, of course, you can do thin, but concrete, because of the aggregate size, you cannot go thin, right? You need to have a certain size. And plus, if you are drying something, then you are cracking something, you know, around the aggregate, on the surface, and you will have that in the isotherm, like it or not. Right? And so for concrete, do we really get to the equilibrium where all these considerations that we make that are at equilibrium really applies? Roland.
So my mistake is the time scale. We have too many directions, but okay. Time scale wise, I mean, you know, when all the discussion we had up to now were onto this reversible thing. So we were elastic, right? When talking about cement, when we look at the capillary force, so we have a very granular, that's the work of Katerina Guanidou and Emmanuel Delgado and so on, about the granular cement at the meso scale, right? We have big pores and grain that are interactions, very good. But then we put some water in that thing and study the capillary deformation. So we could do it, but then we realized that we were creating plastic events everywhere. Not very much in magnitude, in amplitude, but they are like everywhere. So in the end, the paste after one cycle of adsorption is not the same as from the starting point. So we haven't investigated the cycling over time, but clearly this is a very interesting problem because we are entering into the plasticity. And then we never published that, but Katerina did some kind of deformation of the paste with water and so on. And actually, obviously, guess what? The pores are the cracks. They became the starting point of cracking, for the cracks, because they are weak points of the material. So if you are nesting some kind of stresses there and there and there, then you can propagate a crack. So this is, and that is over time because you need cycling. So cycling means time. And then come back to morph and so on, and to zeolites. Okay, they may experience some elastic properties. Yes, as I said, the morph 70%, but nothing is perfect. And those are lacunes, they are crystals, they are missing atoms, they are dislocation. And those are the location of every plastic event. So at the end, it's known that morphs will lose their own kind of ability to breathe and do the whatever separation process over time, because the defects are the way where it is an aging process, if you like, based on defects of the material. So morph because they are nanoporous, cement because it's a mesoporous problem, but still, as soon as we have defects in somehow misorganization, we start nesting those plastic events, and then you can actually help the failure of the material. So in a very irreversible way. So yes, is it linked to the fluid? Yes, of course, because we're dealing with that. It's not. I'm not talking about flow per se under gradient. I guess when you impose a gradient, it's obviously
right.
It's even
very
Great.
good. Any last question from the audience, and then we move to the vote? Anybody? Okay, I think it was a great discussion, and so now we have a few questions for you. So please go to that polev.com website, put Biot-Bazant CO685 that you see here. And there will be a few questions that we ask, and we want you to vote. So we'll give you 1 minute to get ready. It was thank you, Gilles. Thank you, Roland. That was a great debate, great discussion. Hopefully, we will make an example for future conferences to get the debating and
we were not
disagreeing.
We were not very opposing, but okay.
No. I don't know. I started on one side. I think I moved to the other side during this debate. Okay, so I think we can go to the next slide. I say. All right. So this is the question. Can you remove the top right? Do you think that a review paper on this topic would be beneficial? Right. This is to pressure the two debaters to then, after the conference, to collaborate to write a review paper on this topic.
That wasn't expected. Huh?
I know, Roland. I know that's. But
That was a
I
trap.
think we feel that those topics really are hot topics, and it would be very important that we really set this on. Of course, there will be the presentation that will be archived.
I need a draft.
Well, but okay, this is overwhelming majority. 94% says that it is beneficial. So now you have the endorsement of the community, Roland and Gilles, and so you have the responsibility to respond to those requests from the community.
And the more you talk, the more that number increases, actually. You know?
I know.
So stop talking.
I know. Okay. So
You pushing?
I would like to see who said the 5% said no. I don't know. Okay.
My friends.
I don't know. Either your friend because they don't want you to work, or they don't like you. I don't know.
Your real friend vote no.
Exactly. Thank you for the summer, guys. Thank you.
Right. Okay, let's move next. Okay, did this debate impact your view on solid fluid interaction in porous media? Yes, somewhat, no. Okay, let's keep. Hopefully, the A will stay ahead of the B. Otherwise, we failed our missions here. Oops! It's getting closer. It's getting closer. Okay, a few more seconds for everybody to vote. And okay, I think maybe let's stop here. Otherwise, we go ahead. And I think the last one is now to decide whether Gilles is winning or Roland is winning. They don't win anything other than writing the paper.
Yes.
But still, I think
the one who is winning is writing the paper, right?
No.
Let's do this. Whoever wins, write the first draft.
Initiate the draft. Okay.
Yeah, and the second one, you see? Ah, shit. Okay.
Yeah, I told you.
It's getting close, guys. Yes, it's very true.
And the winner is.
It's closer than I thought.
Yeah, you see? Yeah, very good. So, Gilles, you write half of the pages, okay?
No, 40%.
40%. Okay.
I think we can use this as a page breakdown for you. Okay, thank you. 66% for the false, 30% for the so definitely Roland is the winner. And thank you. It was excellent. So please join me in thanking the speakers. Oh, perfect on time is 12:45. This closes this plenary session. There will be 2 additional parallel sessions. I know for some the time is getting difficult for you to attend. I hope we will see you in those sessions. Of course, keep in mind that we are recording all the sessions, and eventually you will have the opportunity to listen to the presentation, to all the presentation at your time. Thank you again, everybody. This was great, and let's continue this conference with the same excitement and energy. Thank you very much. Bye-bye.
Bye, guys. Thank you.
Bye-bye.